This is video 3 of class 4 for ME370, and we introduced pressure vessels in video 1. In video 2, we introduced thin-walled approximation, and here we are in video 3. We're going to do an example, and this is a problem out of Philpott's Mechanics and Materials, and we say that a typical aluminum alloy scuba tank, so like Scuba Steve, is shown in the figure. The outside diameter of the tank is 175 millimeters. The wall thickness is 12 millimeters. And we say if the air in the tank is pressurized to 18 megapascals, we want to determine the hoop and longitudinal stresses based on thin-walled approximation and the normal stresses on a stress element on the inside of the tank based using the thick-walled formulae. And compare, right? So I'll ask problems often where you have to do some comparison. So be on the lookout for those. When you do that, I want to have a statement that this one is this percent larger than that one, right? So you have to have that kind of relationship. You have to tell the percentage, and we got to make a decision on what the comparison is based on, right? So let's take a look at this example problem here. And let's make sure that I did this one out correctly. And I think if I might extend the video by pausing and do a SolidWorks simulation of this problem. That'd be a good idea. I like that idea. Okay, so it's a value added thing. So let me write down what I know here. First off, the outside diameter of the tank is 175 millimeters. So I know that I often will want to have the outside radius of the thing, so I take 175 divided by 2, and I get 87.5 millimeters. The inside, therefore, people mess this up all the time, so pay special attention to this. A lot of times what people will do when they want the inside diameter is they'll just subtract the thickness from the outside diameter, right? When somebody wants the inside diameter, they will just subtract out the thickness. It's 2 times the thickness you would subtract. Or you would take the outside radius and subtract out 1 of the thicknesses. So it's 1 thickness if you're subtracting it from the radius, 2 thicknesses if you're taking it from the diameter. But you'll probably make that mistake. Almost everybody does. So we subtract out 12 and we get 75.5 millimeters is the inside. We might want the inside diameter for something, so we're just going to multiply that right there. We could have just as easily subtracted out 24 from 175 because it's the thickness of 12, right? But we'll just go ahead and do this and get 151 millimeters for that inside diameter. Now, a good thing to check all the time is to find what R, I did it again, T over R. And then people ask, well, which R should we use? Well, the truth is, use either one. If it magically, it's like one of them's above 0.1 and one of them's below 0.1, you're going to go, let's go for we could use the thin-walled, but like write down a little caveat at the end of the thing. But here we have 12 divided by 87.5, that's the outside radius, and we get 0.1371. That's more than 0.1. So we should actually use a thick-walled approximation. So that's the out. If we were to do it to the inside radius of the thing, we get 12 over 75.5. We end up with 0.1589, and it's larger than 0.1 either way. So it didn't really matter which one we did, but if it's close, maybe try it both ways and see what the difference is. But we know that this is not a thin-walled pressure vessel. We should use thick-walled equations. We're going to do it both ways because that's what the instructions told us to do. It said thin-walled and thick-walled, right? Part A and Part B. So we go through Part A, and I'll get the I think I'm going to say, we didn't say the location where we were going to get the stress, right? It does say for an inside thing on here. So I'm not sure when I'm making my comparisons if I should do it. I should probably use the maximum one. But let's see what the difference is. We're going to take the average one. Let's see what the answers are. So we got P di over 2T. So we get this. And by the way, notice when we have these equations that we have pressure times a length term, which is the diameter, divided by a length term. So whatever the units are, we don't have to be careful with the units, really. As long as we use the same ones for this, we're just going to end up with whatever we use for here, right? So we can actually be a little more uncautious. I'm trying to think of like cavalier. There you go. That's what I wanted to say. So we have the inside diameter of this thing, which should have been 151 onto the thing. And I think actually some of my numbers are going to be wrong, right? So this is the average on here, and I have to. I should have fixed this. It was on my mind. I seem to recall having messed this up. And the thickness is 12, right? So what are we going to find? We're going to get 151 times 2 divided 12 divided, and we get that this is going to be, oh, and by the way, this megapascals, right? So these will be megapascals. We'll get 113.3 megapascals right there. Now, we got to go to the what if. What if we get the max now instead? We go P di plus T divided by 2T. So 18, and I should have put a millimeter and then a millimeter there. I was going to show how they cancel out, but I'm not going to leave off the units onto the thing. So I get me 151 plus my 12 divided by 2 and divided by 12. And I say I got 122.3, right? So let's see, 18, 151, 12, add them, multiply them, divide by 2, divide by 12. And so I get 122.3 megapascals. 122.3. Interesting. Okay. So like if we were going to say, well, what's the difference? Let's say that the average was going to be the correct answer. So we subtract that out, and 113.3 we divide. So there's going to be like about an 8% difference, right? This one is 8% greater than that. That's a significant amount, right? So just giving an idea of what the values of these things are going to be. Let me get the longitudinal. No, I could actually just cheat if I wanted to, but I will not. And we'll go 4T. So we say that we go 18, 151, 4, and 12, and I end up with, I say that it's 65.63. It should just be 1/2 of this, right? So if I were to do that, and I think I got that wrong. Let me double check this. 151, 18 times 4 divided, 12 divided. Yep, I wrote down this wrong somehow. Oh, no, I got it. Okay, this is right. There you go. 56.63 megapascals. And by the way, these are all tension. By the way, maybe I should make that clear. They're all tension. They're all trying to pull the thing apart, right? And it's only the radial one that would be in compression, right? So these are the ones that's based on the correct equations right here. I also included, for whatever reason, in my notes, I put the outside diameter too. But I'm just going to keep. I think I'm going to get rid of bringing that up. Okay, let's see. So these are really the answers that we're looking for, and this is also tension right there, right? Because we didn't say specifically which one we were looking for, the inside or the outside or the average right in here. So if I was asked this question and we just stopped right there, I'd probably give the average as the answer and give the longitudinal right there. Those would be the answers to the thing. But let's do it for the thick-walled right here. Okay, so the equation is now going to be RO squared PI divided by RO squared minus RI squared, and then 1 plus RO squared over R squared. And remember that R depends on where you're looking. we said right here it was on the inside surface of the tank. So let's go ahead and we're going to use the inside radius right there. Right there don't indicate, there's no subscript in right there. So we get a RO is going to be 87.5. We said up above. Remember, right up here, 87.5, and the pressure is 18. And the units work out the same thing too, right? Because there's whatever units you used here, and you just make sure you use it there. And it's just, this is what these are in megapascals, so the answer would be megapascals. Here we go, 87.5 squared minus, and the inside radius was 75.5 squared, right? And by the way, probably a good idea just to calculate that separately, right? Because it's going to be, that's what the longitudinal is going to be. And then we have 1 plus, and now we have our 87.5 squared divided by our 75.5 squared. And what we end up finding, whoops, I don't want to make it look like this right here. I can say that right there is going to be our 52.46 is going to be what that answer is right there. But I'll say that my tangential on the inside surface is going to be 122.9 megapascals in tension. And compare that to what this one said. This is a thin-walled approximation. Wasn't too bad, right? I say that that's actually a 0.5% difference. I think we're going to say that here at the end. But my longitudinal here is, I already said 52.46 megapascals, also in tension, right in there. Right, it's just going to be this part of it right here. Notice that this thing is greater than 2, right? Because this is 1 plus, and we have a larger numerator than denominator, and we're missing a parentheses. So this is going to be just slightly bigger than 2, multiplying by this, as you would see. And notice that let's compare this longitudinal approximation, 52.46 versus 56.63 megapascals. So the part C of this thing, as we would see, is that the thin-walled approx is 0.5% greater for hoop, and that laziness is 8%, right? So we say 8% because this right here, if we, 8% greater for long. The word longitudinal is apparently too long to write. So what I'm saying, but make sure that I'm noteworthy just in this general type of thing that we would care about. We would say, we're saying that the thin-walled is the one that we're going to compare against the thick-walled, right? So it's greater, it's greater than the thick-walled, right? The thin-walled is greater than the thick-walled. So we take 56.63, subtract out 52.46, and then divide by 52.46, because that's the thing we're using as the means of comparison, right? So just by numbers, we'd say that was 56.63, and subtract out 52.46, and then divide by 52.46, and we get 0.0794898%, right? That's good enough, because we're just trying to make a judgment onto the thing. We're not doing some kind of scientific survey. So let's see what we could do. I think I will. Otherwise, if the video just ends, other things came up. But I'm going to make this in SolidWorks simulation. And maybe I should go through this as a tutorial of the steps that I would go through. Maybe I will. So let's see how that goes. Taking a chance. Let's see how long is the video. The example is now 14 minutes, which actually would be a good length right here. So can I get rid of that? Sure. All right, so I'm in my computer at work, and I'm going to create a part. And I don't think I have, I'm not sure up to this point in class 4 in the semester, I don't think I've done a SOLIDWORKS simulation tutorial. And this one might be a little more advanced than what we want to do when we first get introduced to it. But anyway, if you're, for this one, we're going to make a pressure vessel. And so there's like some of the more advanced stuff that I'm describing you'll see here in a second. But let me think. When it comes to finite element analysis, you don't have to do a complete model of a piece. But I might anyway. Maybe. I don't know. I'm trying to decide. I'm making decisions here on the thing. So I'm going to make a, I messed up. Let me see. I got to switch over discard changes here. And let me switch over into millimeters. All right, so I'll go into I'm changing my units into millimeters. All right, so let me go back. I'll go to my right view, and this is actually a good thing to be doing so that you get kind of a better sense of how big the dimensions of stuff are, right? If you're going to say, like if we said that the thing was 175, let's see, so we got 175 millimeters, and then it was 12 millimeters was the thickness. So I'll go like that right there. So we got 12 millimeters. So it's nice. It's good to kind of like see what these proportions are, right? You get a better sense. How big are we really talking? And I can see that actually looks pretty thick. Interesting. All right. So we don't know how long this thing is. So we're just making some kind of judgment onto it. For this particular thing, I'm going to go ahead and model the whole, not the whole thing, but like half of the piece. I'm going to make it, let's see. Let's make it 500 millimeters long. Is that going to make too long? Yeah, that's unnecessarily long. Let's make it 250 millimeters long. That's fine. Okay. And all right, so we made like a little tube here, and I'm going to put an end cap on it, and I'm going to put like a some of the view of the thing, the original view of the piece kind of made it look like it was let's just say that it's flat. Let's just make it flat. It's not going to hurt anything. So make it flat. So it's easier to model. It'll have some amount of weird things are going to happen at the corners. Is what you're going to see, some high stresses at the corners. So let's see. Am I in a sketch? I wanted to make a sketch. All right. So while I'm in a sketch, I'm going to grab that outside circle. Did I grab it? And I'm going to hit convert entities. Boom. And that's what I did. And then, so I'm out of that. I'm just going to extrude that by just the thickness right there, right? Boom. So now I've made the thing. It's 12 millimeters thick everywhere. And, I'm going to try to avoid some of those stress concentrations that we're going to talk more about what a stress concentration is, but they show up in FEA all the time. So I'm actually going to put a fillet in here. And, I might make this a 6 millimeter fillet. And I'm going to make it a 12 millimeter fillet on the outside. I don't know. Why not? Is my computer really this slow? This might make the video way too long. Okay, so I'm going to let me put the fillet back onto this outside, and I'll make this a 12 millimeter fillet. Maybe I should have made that double on each of them. I don't know. But anyway, okay. So here you go. I got my piece, and my dimensions are correct. And this is not necessarily a thing, but I like to make the background white. I think it makes it easier to see the thing. It also gets rid of some shading things. All right, so if you didn't already have, this thing says simulation, and you wanted to do the same thing I'm doing, you'd go underneath Tools and go to Add-ins. And because we have an educational version, we have like a whole bunch of stuff that you wouldn't have if you just had the base unit. You'll see that they have SolidWorks simulation. You click here. You can also click on this so it'll start up every time. Right. But anyway, I don't need to do that. I already have it on. But you could see that I have very slow response time. It's making me sad. So I'm going to go to simulation up here, and I'm going to hit study. And it's got there's a bunch of different choices that you could have, but they kind of know with the model that we're looking at right here. All we have to choose from is static. That's all we need. And to make this smaller, quite often all I would do is take like a little section of it, and I would change the boundary conditions on the different edges to the thing so I could make a smaller model size. But I'm not going to do that today. And so we go down this list here on the left, and we start adding things to it. All right, so first we have the part, and I right click on it and I get material, and they told us it was aluminum alloy. They didn't tell us what kind, but we'll just pick out an aluminum alloy right in here. A very common one is 60, where we got our 60 versions right here. 60, 61, very, very common. In fact, they have a couple different 60, 61s with different things. But we don't really care about the strength of it. It's really just the elastic modulus and Poisson's ratio that's getting used in this right here. And I hit apply, so now it knows that it's aluminum. It might even change what the color of the thing is, but you can see right next to it says aluminum. Connections, they don't count only when you're doing an assembly. So now we go to fixtures, and I am going to make it easy by making a fixed geometry. These are what we consider boundary conditions, and I am just going to fix it right there, right? And say OK. And then for loads, I'm going to right click and go a pressure, and I'm just going to place it boom, boom, and then I guess I should do it on this edge right there. Yeah. And you see that it's we can't go megapascals. There you go, megapascals, and we'll go 18. And you notice it's a good idea to look at all the arrows right there. They're all pointing outwards because we don't want it to accidentally go the other direction. And we're going to say that okay. All right, so that was pretty easy. And then we're going to go to mesh, and I'm gonna get the default mesh because we're not trying to do anything fancy. We're just kind of this is just a what if kind of idea right now. And so I'm just going to create a mesh. Let's take a look at the mesh before we hit run, but we can see how crude it's going to be. And we'll mention just quickly, this, for many things, it's a good idea to have more than just one element through the thickness, right? So that's you could argue that's two elements through the thickness. I think it's only really one element through the thickness, but it's not a whole lot, right? But let's just hit run and see what happens and look at the kind of results that we get. All right, so we can already see that like my computer is really sucking wind right now. So it's probably because I have too much stuff saved. I need to purge some things. I need some that virtual memory. But let's see. I'll go up to the top and hit run. So hopefully it's just the graphics that are really slow. There you go. It solved it. All right. Now to interpret these, we want to right click on that results. It's showing the stress right now. And let's make it into the range that we think we're all right. So first, the units that we want to see are probably megapascals, because that's what we're used to. And these other things right up here, I'm going to go to settings. Yeah. And I like to see a discrete. It's easier for me to tell things apart. And I'm also, okay, so now I go to, I think, chart options. Yeah, I'm going to show my min and my max, although there might not be, yeah, they're going to be right there on that interface between those two pieces. So those aren't like reliable stresses. In fact, look at that right there. You can see the amount of stress that's taking place. And the type of stress that we're looking at right now, let me go back to settings, on to definition. We're taking a look at something called von Mises. We don't really define what von Mises stress is until we're in like chapter 5, right? So we're going to take stresses. I might need to refresh myself on how to do this. I want the stresses in the, well, unfortunately we have a cylindrical thing here. So I could go the X direction, which is going to be that direction right there. And that will be longitudinal stress is what we will find from that. So let me go ahead and just do that. And there's longitudinal stress. And let me edit the definitions for longitudinal stress. Or no, I'm sorry, not the definitions, but the chart options. You can see that it does vary with the length, and it shouldn't. So we really need to, the place that we would want to analyze really needs to be away from where the connections are made, or where this transition from being being the end cap, right? But let me take a look at the scale right there, so it's easier to tell by way of color what these things mean. And it looks like the largest value that we have for any stress is like 122 or something. So I'm going to make the maximum here be 120, and I'll make the minimum 0, because we don't really expect to have any compression taking place. But you'll notice that the colors have changed rapidly right along where we attach the thing, right? There's actually a couple of number of reasons. One of them is that we're also constraining it from getting larger right there. So that's going to be a defect in what we're looking at. So when we go to actually take a look and kind of figure out what the values are, we want to pick some place that's kind of far away from where the boundary conditions are applied, if we're going to try to understand what we're looking at. And I'm starting to almost regret that I did this, but that's okay. Let me do the section clipping. All right, so section clipping. And let me choose as my plane, clear the selection, and I'm going to choose my right, and then I'm going to offset it. No, other swap directions. Nope. Swap directions, I want to go here. Well, how do I do that? Where are you? Can I make this negative? Yes, I can. Okay. So like right about there is where I would start to go and start to try to look and see what are my values, right? So I can kind of see, you can't see from the scale very well, but I could go for my plot tools, and I want to probe. And so I'm going to pick like somewhere like right in there, and somewhere right in there. Like I could start to pick little points off, and you can see that I'm getting right around 53.5, 53.6. Yeah, there you go. 53 is what I'm getting compared to what I'm predicting in my, I predicted 52.46 longitudinal stress. So, hey, this is confirming it, but with with these. Now, I might want to pause my video for a second. And the video has probably become too long now. I had another 14 minutes worth of stuff. Let me pause the video. I want to change. I try to remember how to change the display output so I could make it a polar display. So now we can get better way to show what the hoop is. So 1 second. Okay, so I relearned how to do that. Yeah, I needed an axis in here in order to do that. All right, so I could actually, I'm going to go ahead and edit this one. I could create a whole new results here. So under definition, I want to go in the let's see here. It wants me, it's asking me for under advanced for that axis. Let me put it in there. and I'm going to see, it usually gives me like a little, let me see if I hit OK, if it's going to give me that display now. I think I'm trying to, let me see if this thing, does it tell me more? Let me go edit definition, and here in advanced. A lot of times it'll tell me something different, like right in there. Let's see what my results are for the Y direction. Usually there should be like a little symbol down before. Let me run this again. A lot of times that's what it needs to. Oh, there it is. There's the little symbol down here at the bottom right-hand corner, right there. Okay, so that symbol is telling me, I believe, that and it should have, this thing stayed the same, right? Yeah, I think the Z is going to be, let me see, I'll edit this. Let's just try these out. Let's see, Z I think is going to be the radial. Is that true? No. No, okay, so Z is probably going to be the longitudinal. That's what it was before, right? That's the one that was like, I'm looking at the, you probably can't see how small this is here, but that thing down there is looking like the Z right in here. And so let me edit this, and let me take a look at what the X is going to be. The X is probably going to be the radial. Yeah. So like if we were going to do plot tools and the probe, and we're going to pick some place like on there, we could see that it was like really small, something really small. Okay, so right there, see it's getting negative. It's getting close to that. It's like negative 16 right in there, and right there. There you go, negative like 16.75. We're right there. It's like 18. Basically, right? So that right there, when we're under the X direction for this, so the Y direction must be the normal stress here, and okay, so that right there should give us a pretty good interpretation of the hoop stress. And once again, it's messed up because of the end right in there. And but this is, the thing is expanding out in this direction. It's basing on that. So let's see. Let's get our plot tools and probe, and we could pick a point right there. We see we get 125, and right here on the outside we get something more like 110. Right there, so somewhere in between there. So we're saying that the maximum should be 122.3, and we're getting 125 right here on the inside versus the outside surface. And as I mentioned, I should have made different choices with the way that I was representing this, and I could fix those things fairly easy. Maybe I'll do that like really quickly and show you what the proper way of doing this model was. So like I'm actually probably a pretty good example of what not to do in the FEA. But I'll reset this, or I guess I'll turn it off right there. Yeah, okay. So let me pause this and then fix it. I'll pause the video and then fix that. Hopefully it'll pick right up. I won't have to redo everything. Okay, so I've changed it to just a quarter of the model. It's all you really need. And then I put these what they call symmetrical boundary conditions on here, and then ran it with, once again, this is the very low res mesh that we have onto the thing. So we run it, and so here are these are the hoop results. Right. Once again, my output coordinate system I've changed so that they are now in cylindrical coordinates. So if we take a look at like the cross section, you can see like right here where the boundary conditions are, they don't change all that much across there. So if I want to get a more refined mesh, let me try that out by creating a better mesh. Here I'll go create mesh, and we'll lose all the results. And I'm just going to throw caution to the wind and hit fine and have it mesh. And let's see how many elements. All right, so we put quite a few more elements through the thickness of the thing. That's going to improve the quality of our results. If you have something that's thin most of the time, you actually want to use plate elements. Are a much more advanced element to use in most FEA codes. This might take a little more time to run because there's a lot more degrees of freedom on the matrices that has to do the thing. And it's going to make a liar out of me and just solve it like really quickly. I don't know. Is it stuck at that 27.3% that I see a lot of times? Oh, there it is. Okay. And so let's see. Well, the colors didn't change all that much through the length of this thing. But let me see by going through, I could do more plot. I could do list selected. And what you could do from that is you could connect this edge right here, that edge, and we could plot what that is. Let's see. Okay, these plots are always terrible. Let's see. I say they're always terrible. It's not very fair, but you can kind of see here's the variation of stress throughout the thickness of this thing, and you can see that it's starting on the outside in the low 100s, like 10. I don't know. Let's see. Is it going to give me a point right there? Yeah, it's like 105, right? And then up here at the top, it's like 122, 123. That's really close to what we calculated by hand. That's pretty satisfying, right? And this time I didn't do the cutaway for the thing. You can see as it starts to get near the end, it's a much more complicated thing that's taking place here at the end. Because of this arrangement right here. It's not necessarily something that we'd be able to figure out by hand in a short amount of time. Maybe if we were very motivated to do it, but we could see, the length of this thing, and it's gonna. If we just change the length of it, nothing would really change up at till still we got towards the end, in my opinion. All right, and let's see. Let's also change it to see what the longitudinal is. I bet the longitudinal is going to be pretty good here. We'll edit the definition and change this. I forget. I think it was the Z. The Z was the one that got close. Yeah. So we're probably going to have a pretty. It should be actually almost exactly right there. So I could just I need to finish my sentences. If we were to take these little probes right here and just start plotting out at different little points right here, boom, 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 boom. Let's see. We would see that we get 52.4, 52.4, 52.4, and what do we predict that we were going to get? 52.4. So you can see some of the, we've used a computer simulation here. You own SolidWorks, or you've had access to SolidWorks, and you can try some of this out. Probably not on your student version on your personal computer, but you can go to the lab computers. You can remote into the lab computers, and they have the full educational version that'll include this SolidWorks simulation, and you could try some of this out. Now, once again, there's more advanced stuff going on here, so it's not like the first one that I would say throw you in the deep end and say start messing with. It does have a lot of interesting things that we should learn about. I do have a section on finite element analysis that's coming up in Chapter 4, where I'm going to ask you to do a task in SolidWorks simulation. So this is sort of like a little bit of a teaser, but I'm going to save this thing and maybe use it in class to try to discuss some of these ideas of these stress states that we're trying to calculate by hand. We're also going to calculate them by computer, but we want to make sure that we can do it both ways. so that we could confirm the simulation stuff is viable, that we had a viable outcome. And you'll notice as an example, I just went ahead and threw a bunch of stuff in there, and I got wrong answers because I didn't model it correctly. So you have to be careful with these simulation tools that you can just throw something up against the wall, get a result, and not to be a correct result because you didn't. A lot of times because you didn't put the boundary conditions in the right way. So that's it for today's, for that example. And it went long, but only because I wanted to include that simulation thing in it. I don't know if it was worthwhile, but maybe somebody will get something out of it. I'll continue on now with 3D Moore circle.